What if I told you that NASA has just released new images of an interstellar object promising to finally unlock one of the greatest cosmic mysteries? But instead of answers, what they found is something so bizarre, it defies everything we thought we knew. Imagine an object that's too large to behave the way it does, too chemically strange to be natural, and so statistically improbable it shouldn't even exist. Intrigued? Well, hold on tight, because what happened next will leave you questioning everything. Right now, scientists across the globe are staring at their screens, unable to believe their own eyes. The data is in, the numbers have been crunched, and the reality is everything we thought we understood about 3I Atlas has just been completely turned upside down. If you're captivated by this mystery and want to dive deeper into more mind-bending cosmic stories, don't forget to hit that like button and show your support for exploring the unknown. Every click helps keep this search alive. For months, astronomers waited for this moment. They knew that the James Webb Space Telescope would soon capture a true image of 3I Atlas, the solid core hidden beneath its glowing coma of gas and dust. They believed that once they could finally see it clearly, the endless debates would end, the mystery would be solved, and we would finally understand what we were looking at. But instead, when the images came in, everything got worse. Instead of closure, the images revealed a nucleus larger than expected, a structure that simply doesn't fit with anything we know about comets. Its chemistry refused to follow any known patterns, and its behavior, well, it didn't match anything that scientists associate with natural comets. What was meant to solve the mystery ended up expanding it. And now, the scientific community is faced with an undeniable question. If 3I Atlas doesn't behave like a comet, then what exactly is it? Stay with me, because the journey ahead will challenge everything you thought you knew about space, comets, and possibly what's traveling between the stars. For the longest time, scientists couldn't directly observe the nucleus of 3I Atlas. This limitation shaped most of their assumptions about the object. From Earth, the object appeared wrapped in a bright cloud of gas and dust, known as a coma. This coma reflected sunlight and hid whatever solid body was beneath, forcing astronomers to guess at the size using indirect brightness models. In other words, they were trying to figure out the size of an object based on how bright it appeared from a distance. Think of it like trying to estimate someone's height based on the shadow they cast from miles away. Sure, you can make an educated guess, but it's still just a guess. But the real breakthrough came with the James Webb Space Telescope, which was designed to see things that other telescopes couldn't. Operating in infrared, far away from Earth's heat, Webb detected faint thermal signals that visible light instruments often missed. After 3I Atlas passed its closest point to the Sun, its activity slowed down enough for Webb to isolate the nucleus with much greater clarity. For the first time, what was once a blurry object surrounded by gas and dust was now visible as a defined body with measurable properties. And this, my friends, is a game changer. The key here is the difference between observing a coma and a nucleus. A coma reflects current activity that can fluctuate wildly, while the nucleus represents the object's true structure and mass. By focusing on data taken after perihelion, Webb allowed scientists to move past the guessing game and replace assumptions with concrete numbers. It marked a turning point because every major theory about 3I Atlas depended on how big and heavy the object actually was. When the numbers finally came in, they did more than refine earlier estimates. They threw out many of the assumptions scientists had worked with for months. Now, all the theories built on those smaller, lighter nucleus models looked fragile at best. The image did not bring closure. It gave us something more important. a solid reference point that couldn't be ignored. But here's where it gets even more fascinating. Once the nucleus was clearly visible, something unexpected happened. Scientists started to question its behavior. How could an object this size still behave as though it were much smaller? The newly revealed size of 3I Atlas forced scientists to ask an even bigger question. Why was this massive object behaving like something much lighter? Stick around, because we're just getting started. What's coming next will blow your mind. Let's pick up right where we left off. Now that the size of 3I Atlas has been measured with unprecedented clarity, scientists were forced to reconsider their understanding of the object. The newly revised estimate places the nucleus at about 2.6 kilometers across, with some suggesting it could be as large as 3 kilometers. At first glance, that might seem like a small change. But let me explain why this seemingly minor difference is actually a game changer. When you're dealing with objects millions of miles away, a few hundred meters might sound insignificant, but in terms of physics, that's enormous. And here's why. Mass does not increase in a linear fashion with size. When an object's diameter increases, its mass grows exponentially because volume scales with the cube of the diameter. To put it simply, if something is 3 times wider, it can be up to 20 times heavier, not just 3 times. That is a massive difference. This is why the new size estimate of 3I Atlas sent shockwaves through the scientific community. An object this large isn't just slightly bigger, it's far more massive, far more resistant to change, and far harder to move than scientists ever expected. And once that new mass was taken into account, every model about 3I Atlas had to be reworked. For months, scientists had believed that 3I Atlas was a relatively light object, and this assumption shaped nearly every theory about its behavior. Those early models assumed the object was no bigger than a kilometer in diameter, leading scientists to believe it would behave like a light comet. But now, with the updated measurements, 3I Atlas is much heavier, much denser, and much harder to move than anyone anticipated. This discrepancy makes it clear that earlier theories simply don't hold up anymore. If 3I Atlas is this much more massive than we thought, then many of its observed behaviors don't add up. For example, a smaller object would have an easier time reacting to solar radiation or the pressure from its coma. But a much heavier object should behave quite differently, resisting these forces with far more inertia. And that's where things get tricky. To put this into perspective, let's look at previous interstellar visitors like Oumuamua and 2I Borisov. These objects were much smaller, and their behavior aligned more closely with existing comet models. But 3I Atlas? It's in a category of its own. Not only is it larger than we expected, but its scale pushes it outside the range where the old models still make sense. So the question now becomes, what are we really dealing with? Is 3I Atlas just an unusually large comet? Or is it something entirely different? It's a question that forces scientists to reconsider how we classify interstellar objects. The first major consequence of this size revision was the collapse of several long-standing explanations. If 3I Atlas is truly this massive, many of its behaviors can no longer be explained by standard physics alone. For example, when scientists looked at its movement, they couldn't reconcile the fact that it was behaving like a much lighter object. This created a huge problem because it suggested that something far more complex was going on inside 3I Atlas. The shift in thinking didn't stop there. It also raised new questions about the object's origins. If 3I Atlas isn't a typical comet, then how did it form? How did it evolve? And more importantly, could there be other objects like it, lurking in the depths of space, waiting to be discovered? Now, Here's where things get even more intriguing. When scientists looked at 3I Atlas from the perspective of its size and mass, they began to realize that something else was at play. The object's behavior wasn't just strange, it was outright confusing. And that confusion only deepened as new observations continued to challenge everything scientists thought they knew. This is where we enter into the realm of non-gravitational acceleration. In simple terms, this means that 3I Atlas is moving in a way that cannot be fully explained by gravity alone. Typically, comets change their motion as they shed gas, but the scale of this object should make that process far more difficult. If 3I Atlas truly is this massive, how could something this heavy be changing its trajectory so easily? The answer, as you might guess, is still unclear. While some scientists suggested that outgassing could account for the observed acceleration, others pointed to the object's internal composition. Maybe something else inside 3I Atlas is causing it to move in ways that defy the laws we thought we knew. Whatever the case, the motion of this object is becoming a mystery that goes far beyond what we thought was possible. But that's not the end of the story. The strange behavior of 3I Atlas doesn't stop with its size and motion. There's also the issue of its chemical composition, which has turned out to be just as puzzling as its size, and we'll get into that in the next part. Now that we've tackled the unexpected size and mass of 3I Atlas, let's dive deeper into its behavior. As 3I Atlas moved away from the Sun after its closest approach, astronomers expected the usual pattern to emerge. For most comets, activity decreases after perihelion, the point where the comet is closest to the Sun, because the heat begins to subside and surface reactions slow down. However, 3I Atlas did not follow the usual script. At first, its overall brightness seemed to dim rapidly, leading scientists to believe that the object was finally settling down. But this apparent calm was only surface deep. When astronomers looked more closely, they detected subtle pulses of brightness that didn't fully fade. These pulses were not consistent with the usual behavior of comets, and their timing didn't line up with the object's rotation period. Typically, comets rotate, and as different parts of the surface come into the Sun's light, their brightness fluctuates accordingly. But these pulses didn't follow that simple pattern. This mismatch led scientists to wonder if something deeper was at work. The object's surface might have appeared calm, but the irregular pulses suggested that something inside the nucleus was still responding to energy, but in an uneven, delayed way. In essence, it was as though the object was not simply cooling down like a typical comet. There was something else going on beneath the surface, something that was not immediately obvious from the outside. And this brings us to the idea that 3I Atlas might have a more complex internal structure than we originally thought. If the nucleus contains regions with different densities or compositions, it could be that energy is being released unevenly as the object cools. Some parts of the nucleus could retain more heat, causing them to release energy long after the main heating phase had passed. This internal complexity could explain the unexpected pulses in brightness and further complicates our understanding of the object. But this is just the beginning. If the internal structure of 3I Atlas is more complicated than we thought, then the next big question is about its chemical makeup. And let me tell you, this is where things get even stranger. As we know, comets are often made up of a mix of water, carbon dioxide, and other volatile substances. But the infrared data from James Webb revealed that the chemical composition of 3I Atlas was anything but typical. As the object moved farther from the Sun, its coma, the cloud of gas and dust surrounding it, began to show some surprising changes. For one, the amount of water vapor in the coma increased, while carbon dioxide decreased. On the surface, this might seem like a normal response to the fading heat, but when you dig deeper, it becomes clear that something is off. The real shock came when scientists detected metals like nickel and iron in much higher quantities than expected. While nickel was present in unusually high amounts, iron, which had been almost completely absent before, began to show up more clearly. This was a huge anomaly because in most comets, the balance of nickel and iron is relatively stable. However, in 3I Atlas, that balance was completely disrupted. This anomaly raised an important question. Why were metals like nickel and iron appearing in such unusual amounts? One possible explanation could be that 3I Atlas is not just a simple ice and dust object. It might have a more complex internal composition, one that doesn't fit neatly into the patterns we've observed in other comets. And this is where things start to get really interesting. The presence of nickel without a corresponding increase in iron suggests that the object might be made of material that has been processed under extreme conditions, possibly involving high temperatures. Such conditions would not typically be found in a natural comet, especially one as far from the Sun as 3I Atlas. The chemistry of 3I Atlas points to something rare, something not easily explained by the models we've used for decades. And while scientists are cautious about jumping to extreme conclusions, the data is hard to ignore. The timing of these chemical shifts also adds another layer of mystery. Typically, when a comet gets closer to the Sun, the heat causes the release of certain gases, and the object's chemical makeup should evolve accordingly. But in the case of 3I Atlas, the most unusual chemical signatures appeared after the object passed its closest point to the Sunday. This reversal challenges our fundamental assumptions about how comet chemistry should behave. As if the strange behavior of 3I Atlas weren't enough, the real kicker came with the discovery of methane. In most comets, methane is one of the most volatile molecules. It's the first to escape when the object approaches the Sun, and it usually peaks near perihelion before fading as the comet moves farther away. But with 3I Atlas, methane didn't follow that pattern. In fact, it did the exact opposite. At first, scientists were puzzled because they couldn't detect much methane as the object approached the Sunday. This was strange, because methane typically escapes before other gases like carbon dioxide and carbon monoxide, but the real shock came after perihelion. When the comet started moving away from the Sunday, methane production increased significantly, even though activity was supposed to be slowing down. Imagine this. You've got an ice cube sitting in the Sunday. Normally the ice would melt first, right? But what if, after the ice is moved into the shade, it starts melting faster than it did in the direct sunlight? That's exactly what 3I Atlas did with methane. The gas appeared in higher quantities after the object moved farther from the Sun, when it should have been fading away. This reversal completely defied the basic thermal behavior of methane. Some scientists suggested that maybe methane had been depleted in the outer layers of the nucleus and only released once the outer material was stripped away. But this idea quickly ran into problems when scientists compared methane's behavior to that of carbon monoxide, another highly volatile molecule. Carbon monoxide had already appeared early and didn't vanish the way methane did. Another explanation pointed to the possibility that 3I Atlas has an unusual internal structure, with pockets of material that responded differently to heat. Perhaps methane was trapped inside the object and only released later when the object's outer layers were worn down. This idea is still on the table, but it would require conditions we've never observed in any well-studied comet before. The real issue here is that methane's behavior doesn't fit with what we know about cometary chemistry. It should have reacted in a predictable way, but instead, it defied expectations. And this is just one more anomaly that adds weight to the growing list of contradictions we're seeing with 3I Atlas. As strange as this methane anomaly is, it adds to a bigger picture that's beginning to emerge. Every new discovery about 3I Atlas seems to uncover more questions than answers. If methane isn't behaving the way we expect, what does that say about the forces shaping this object as it moves through space? And if methane can't follow the rules, then what other surprises does 3I Atlas have in store? Now that we've explored the strange size and chemical anomalies of 3I Atlas, let's turn our attention to its motion. If you remember, scientists have been puzzled by the object's behavior ever since it was first discovered. Initially, many believed that its unusual path could be explained by simple gas emissions, a process known as outgassing. You can think of this like a rocket. When gas escapes from a comet, it pushes the object in the opposite direction, slightly altering its trajectory. This process works well for smaller objects, but what about a massive one? With the updated measurements placing the nucleus of 3I Atlas at nearly 3 kilometers across, the object is far more massive than initially thought. And here's where the problem arises. A larger, heavier object like 3I Atlas should resist changes in its motion far more than a lighter one. In other words, it would take an enormous amount of gas being expelled continuously for such a large object to shift its path. But the problem is this: the observations don't match the level of activity needed to account for the changes in its motion. If 3I Atlas were behaving like a smaller object, then the outgassing would explain its trajectory. But for an object this large, the gas emissions would need to be intense and constant. However, observations show no such extreme eruptions. The surface doesn't appear torn apart, and the brightness doesn't match what we would expect from an object emitting so much gas. So, the big question is, how can an object this massive move as though it's much lighter? Some researchers have suggested that gas might have been released unevenly, creating a stronger push in one direction, but that doesn't quite solve the problem. Others have proposed that heat from inside the object could have built up and been released later, but this idea also falls short of fully explaining the observed motion. The truth is, scientists are still trying to piece together the puzzle of 3I Atlas's motion. This non-gravitational acceleration, where the object moves as if it's much lighter than it should be, is one of the most perplexing aspects of the mystery. And until this can be explained, it leaves an unsettling gap in our understanding of 3I Atlas's behavior. But here's the thing. If the motion of 3I Atlas can't be fully explained by current physics, it's not because the laws of physics are broken. It means that this object, 3I Atlas, doesn't fit neatly into the categories that scientists have relied on for decades. And this realization is a huge deal because it suggests that the universe is far stranger than we previously thought. As we try to piece together the puzzle of 3I Atlas, we are faced with a question that goes beyond this one object. What does it mean for our understanding of interstellar objects as a whole? If 3I Atlas isn't a typical comet, if it doesn't behave like anything we've seen before, then how do we classify it? And more importantly, how do we know what else is out there waiting to be discovered? One of the most striking aspects of 3I Atlas is its sheer size. While many of the interstellar objects we've detected so far have been relatively small, 3I Atlas is enormous by comparison. This raises a critical question. Why are we only finding large interstellar objects now, after detecting so many smaller ones? Shouldn't we have detected the small ones first? If smaller objects are far more common than large ones, then finding a massive interstellar body like 3I Atlas should be a rare occurrence. And yet, here we are, facing an object that is much larger than expected. One possible explanation for this could be observational bias. Larger objects are easier to detect because they reflect more light or release visible material. But this doesn't completely resolve the tension. Modern sky surveys are incredibly sensitive and can detect smaller objects, so the absence of signals from many smaller interstellar bodies raises the question, are we simply encountering rare, large objects, or are we finally realizing just how incomplete our map of the universe really is? What if 3I Atlas is not an anomaly at all, but merely the first of many interstellar objects out there that are far larger and more complex than we've previously imagined? If this is the case, then we might be on the brink of a revolution in how we understand space and the objects that pass through it. And that, my friends, is the most extraordinary possibility of all. As we continue to study 3I Atlas and other interstellar objects, we must ask ourselves, what is out there beyond our solar system? Are we truly ready to understand the full extent of the universe, or are we still only scratching the surface? And what else, hidden in the vast reaches of space, will challenge our understanding of physics, chemistry, and the very nature of the cosmos? This is why the story of 3I Atlas is so important. It's not just about one mysterious object. It's about the questions it raises, the mysteries it uncovers, and the potential it holds for uncovering even greater secrets about the universe. Don't stop here. The universe is full of surprises waiting to be uncovered. Click on the next video and let's continue exploring the astonishing mysteries from the farthest reaches of space.